Good morning. So we're moving on to our next lesson where we're still simplifying radicals, but we'll be multiplying radicals together and looking at some quotients also. And while we do that, just a reminder that you can use the product and quotient properties of square roots together with commutative, associative, and distributive properties when you multiply, divide, and simplify square root radicals. All right, so we're going to be doing a lot of practice here. This first section actually has quite a few in here, just so I could give you a lot of practice. I think there's 13 of them here. So let's start out, and I'll just explain as we go processes to use as you do them. So if we're multiplying together the square root of 3 times the square root of 12, because both of those are square roots, they have the same root, you can multiply the radicand. So you get 3 times 12 is 36, and the good part about that now is you've created a perfect square trinomial, and the square root of 36 is 6. Let's see, number 2, we have the square root of 3 times the square root of 3 times the square root of 9. 3 times 3 is 9, 9 times 9 is 81, and 81 is also a perfect square, and it is 9. All right, let's step it up a little. The next one, 5 times the square root of 3 times 8 times the square root of 21. So this time we have numbers on the outside or in front of our radicals. We would multiply those just like we normally multiply, and we would get 8 times 5 is 40. So we have 40 on the outside. Then the square root of 3 times the square root of 21 is the square root of 63. 63 is not a perfect square, but I do know that 9 is a factor of 63, and it is a perfect square. So I'm going to go ahead and take the square root of 9 and leave the square root of 7 inside. So I get now 40 times 3, which was the square root of 9, times the square root of 7. So this equals 120 times the square root of 7. All right, let's go to the next one. 3 times the square root of 2 times 4 times the square root of 18. We're going to do what's on the outside, and 3 times 4 is 12. We're going to do the radicals. 2 times 18 is 36. 36 is a perfect square. It's 6, so we get 12 times 6 is 72. Switch colors. The next one, the square root of 7 times the difference of 6 minus the square root of 2. So this is where we would apply the distributive property. The square root of 7 times 6, you cannot multiply those together. One's a radical, one is not. So you just have to write it 6 square root of 7. You usually put whatever's not in the square root in front of it. And then the square root of 7 times the square root of the negative square root of 2 becomes the negative square root of 14. Okay, we can't combine these. We'll be doing adding and subtracting later in this unit, so you'll learn when you can combine radicals that you add and subtract. Neither 7 nor 14 have any perfect square factors, so we're done. Number 6, 5 times the square root of mn, and the n is squared. We'll put that in parentheses because we're multiplying that times the negative 2 times the square root of m. All right, we're going to multiply 5 times negative 2 on the outside, and it gives us negative 10. Now we can multiply what's in the radicals because they're both square roots. M times m, that means you add your exponents. So 1m and 1m is 2m. So that gives us m squared, n squared. And we know that m squared is a perfect square. So we get negative 10 to the m, and we know n squared is a perfect square. Half of 2 is 1. So we get negative 10mn. Okay, one thing I forgot to point out when I started doing these was the rule, the directions. Practice. Assume that all variables represent positive real numbers. Because it's telling us that all variables are positive real numbers, we don't have to worry about putting absolute value symbols around any of our odd exponents with variables. So whenever you would see that in your directions, you don't have to worry about your variables having absolute value. All right, number 7. negative r times the square root of r squared s times negative s times the square root of r squared s. Okay, I'm going to multiply what's on the outside first. Negative times negative is positive. R times s is rs. I'm going to multiply what's under the radical. R squared times r squared is r to the fourth. We add the exponents, and s times s is s squared. Both of these are perfect squares, so this becomes rs times r squared times s squared. We can combine these. This is r to the first times r to the second. You add the exponents. S to the first times s to the second. You add the exponents. Sorry, when I took the square root of s squared, that should have just been s. So we would have s to the first and s to the first, and that's s squared. So it's r cubed s squared. All right, number 8. The square root of x times the sum of the square root of x to the fifth plus 7. All right, so we have a radical times a radical, so we add the exponents and we get the square root of x to the 6th. We have a radical times a number, so we just write 7 times the square root of x. The square root of x to the 6th, that's a perfect square. It's half of that, or x cubed plus 7 times the square root of x. And that's all you can do. Let's see, I think I can squeeze number 9 in here before we go to the next little section. The square root of 3a times the square root of 2a times 2 times the square root of 6a squared. All right, so I'll do the outside first. 1 times 1 times 2 is 2. And then I'm doing the inside. 3 times 2 times 6. So 3 times 2 is 6, and 6 times 6 is 36. I have a to the first, a to the first, and a to the second. That's a to the fourth. All right, so 36 is a perfect square at 6. A to the fourth becomes a squared. So we have 2 times 6, or 12a squared. All right, I'm going to come over here. I have, it looks like 3 or 4 more I want to do with you all. Number 10, the square root of 27 times the square root of 3n times the square root of 5n. All right, everything's under the radical. I'm going to go ahead and multiply my numbers. So I have 27 times 3 times 5. Or I can just do, to help me out, what if I just did 27 times 3 and left it as 81? Why would I do that? Because 81 is a perfect square. And then we'll just leave the 5 there. Then we have n times n is n squared. So 8 times 5 times n squared. All right, so now 81 is a perfect square. It's 9. N squared is a perfect square. It's n. What is not a perfect square stays on the inside. So it's 9n times the square root of 5. Number 11, we have 2n. Let me see. Let me start that over. 2n times the square root of 7n, the whole thing squared. Okay, so let's talk about this. 2n times the square root. So this means that I'm squaring everything inside. So this becomes 2n times the square root of 49n squared. Well, the square root of 49 is 7. The square root of n squared is n. And then I'm going to multiply it by 2n. So I get 14n squared. Now, I'm going to look at this in this same problem again to show you, possibly you may see it as an easier way. I do. When you are squaring something that is already the square root, so if you're squaring something to the square root, you basically take those off and you just end up with the radicand. So if you like and know that shortcut, that you know that, oh, if I square something that's to the square root, it just gives me that radicand, go ahead and take that shortcut. Otherwise, you can distribute it through and do it like I did. All right, number 12. I have 2 times the square root of 6x cubed. I'm going to leave that out of parentheses, actually, because it looks like I'm going to be distributing. Let me rewrite that over again. All right, number 12. 2 times the square root of 6x cubed. I'm going to multiply that by 3 times the square root of 8x minus 5 times the square root of 3x to the 4th. All right, so I'm starting and I'm sharing this to this. So I look at the outside of the radical of both. 2 times 3 is 6. I look at what's inside. 6 times 8 is 48. I have 3 x's and 1 x. That's 4 x's. Okay. Then I'm going and sharing it over here. 2 times negative 5 is negative 10. 6 times 3 is 18. I have 3 x's and 4 x's. That's 7 x's. All right. So 48, I know I have a perfect square factor in 48. Let's see. Square root of 40. I know 16 is a factor for sure. 16 times 3 is a factor. So let's rewrite this as 16 times the square root of 16 times 3 times x to the 4th minus 10, and I have 18, so 9 times 2 times x to the 7th. And I'm going to rewrite x to the 7th. What's the most even amount? There's 6, and then there's that one odd one, because I know that 6 of them are a perfect square. Square root of 16 is 4, so I have 6 times 4. Square root of x to the 4th is x squared. So I'm left with the square root of 3. I'll come back and clean that up. Then I have minus 10 times square root of 9 is 3. The square root of x to the 6th is x cubed. What am I left with? The square root of 2x. So now let's combine this. I get 24x squared times the square root of 3 minus 30x cubed times the square root of 2x. It's kind of a funky answer, but that is the answer for that one. Okay, finally one more. Boy, I used every piece of possible space. I'm going to write it right in here. Number 13. 5 times the square root of 2. 5 times the square root of 2x cubed all to the 3rd power. This exponent on the outside is going to the 5 and everything inside. So this becomes 5 cubed. Inside 2 cubed, and 10 to the 3 times, or x to the 3 times 3 is x to the 6th power. Power to a power. We multiply the exponents. We don't want to add them. X to the 9th power. So on the outside we have 125 times the square root of 8x to the 9th. Well, I know that I can rewrite 8 as 4 times 2. And I know I can take 8 x's out of 9 x's and have 1 left. Square root of 4 is 2, so I have 125 times 2. The square root of x to the 8th is x to the 4th. What is not a perfect square is the 2x. What is my final answer? 250 x to the 4th times the square root of 2x. Okay, I'm going to stop here because I need to... there's not enough time. So we'll finish with this and then we'll restart it with part 2.